Hi there, welcome to this brief guide to uncertainty. The only certainty about uncertainty in science is scientists are going to argue about how it should be done. So what I'm going to take you through is how I expect uncertainty to be handled whilst doing practical experiments in diploma physics. So let's think about where uncertainty comes from. If we look at this diagram, we can see if you're measuring the length of this pencil, it lies somewhere between 25 and 26 centimeters. Now we need to think about, there's nothing wrong with the ruler, but it doesn't quite allow us to measure to perfection, but nothing does. So how do we handle this? Well, what we do here, the answer would be to quote the length of this pencil to be 25.5 plus or minus 0.5 centimeters. That plus or minus 0.5 centimeters just shows that it's somewhere within that range of uncertainty from my final answer. So there's some rules, and this short podcast hopefully is going to go through a bunch of rules, and you should use it as a reference point in the future. So, starting off, how absolutely much uncertainty can we call? When you're making a measurement, logic normally says uncertainty should be at least half the smallest scale division. Now that means that if we look at the smallest scale on a measuring device, we're going to say it's going to be at least half of that, because we can say it's kind of midway or kind of not. Increasingly, there's a convention just to quote plus or minus the smallest scale of division. So to accept that smallest value on the measuring device is as good as you can get. The final way that you may come up is to find that the manufacturer has already quoted the accuracy of the equipment. So a digital voltmeter can read plus or minus 0.5%. Now, these three ways allow you to define an absolute uncertainty. But they're all slightly different, and as long as you agree or are consistent and state what you're doing in the first place, there's no problem. So if we look at my first example, what would be the uncertainty on a millimeter ruler? Well, a millimeter ruler would find that it'd be plus or minus 0.5 millimeters. So that's half the millimeter scale. If we go for the more wider used convention now, what's the uncertainty on an ammeter with 0.2 divisions? Then the uncertainty would be plus or minus 0.2 amps, because each of the smallest divisions is what we're going to say we're accurate to. With plus or minus 0.5%, if I had a voltmeter which measured 20 volts, I'd say that 0.5% of that would be plus or minus 0.1 volts. So those are ways that you may decide on your original measurement uncertainty. You're not going to recognise that experimental uncertainty, you're not normally going to make one measurement. You often take multiple measurements, so that can be taken into consideration as well. Obviously, if we take multiple measurements, our value is going to be the sum of the values divided by the number of the values to give ourselves a mean. Now, the uncertainty around that mean often comes up from an experimental uncertainty. So that would be the maximum value minus the minimum value divided by 2, just halved. So let me show you how this would work. If the resistance of a lamp is measured by 6 students, to be 609, 666, 639, 661, 654 and 628, what value would we quote? Well, in this case, what we'd do is we'd calculate the mean, and this is 643. Note that I've rounded here, so I have the same number of significant figures as my original values. The uncertainty is going to be 609 minus 666 minus 609, and then divide that value by 2. And again, that gives me a value of 28.5, which I round to make sure that I've got a similar level of significant figures as my main value, which gives me 643 plus or minus 29 ohms in the end. So, what's next? There's also other forms of uncertainty. We've been talking about what's something known as the absolute uncertainty, and this is plus or minus the value which we've been given. Uncertainty can also be expressed as a fraction or a percentage of the value. So if I have 3.2 plus or minus 0.1, then the fraction would be 0.1 divided by 3.2, so that's the fractional uncertainty. Or I can calculate 0.03, which is the digital number, multiplied by 100 gives me a 3% percentage uncertainty. So there's other ways of showing uncertainty. Where does this uncertainty come from? So there's two ways you can get it. You can get random uncertainties. Human misjudgment is one. Limitations in the equipment is another feature. A lack of reproducibility in the actual measurements. So that means that the value, which the thing we're looking for, is very difficult to capture again. Now, these should be eliminated by a careful and logical approach, and this can include repeating measurements or being as precise as we possibly can. Eliminated or reduced is the general factor there. So those are some random errors, and those random errors are likely to occur in all experiments. We also might have something called a systematic error. Now, a systematic error is something which shifts all the measurements away from the true value. Now, this is something which is more difficult to find out. It could be caused by a slow wronging stopwatch or a wrongly calibrated thermometer. So everything's shifted away. Now, this has an impact on accuracy. And what we can do here is, the best way is to cross-reference with other people's measurements or known values to see if our measuring devices really don't have any systematic uncertainties involved. You often have to combine uncertainties. So in some cases you'll be doing a sum where you've used several measurements and you need to combine these uncertainties. For addition and subtraction, it's fairly straightforward. What you do is you add the absolute uncertainties. So if you're doing a sum which is value y, which is b minus c, then the answer to y, that uncertainty, would be equal to the sum of the uncertainty of b and the sum of the uncertainty to c. Now see, you're summing those even though there's a subtraction calculation, because all you can do is you add, do calculations, the uncertainty only always gets bigger. Here's an example. Calculate 2.43 plus or minus 0.05 centimeters minus 1.43 plus or minus 0.01 centimeters. Obviously the calculation itself should be fairly straightforward. You should recognize the answer is 1.00, but here we've got to remember that the uncertainty has increased, so it's 0.06 centimeters. That's when you're adding and subtracting. Combining uncertainties with multiplication and division, in this case we have to add the percentage uncertainties or the fractional uncertainties. So if we're doing b times c, then the uncertainty of the fractional uncertainty of x would be the sum of the fractional uncertainty of b and the fractional uncertainty of c. I've got a calculation here, 1.02 plus or minus 0.12 kilograms divided by 2.43 plus or minus 0.24. Now what I have to do here, the calculation itself, my answer is 0.42. But now my uncertainty is going to be 0.42, which is the value I know multiplied by the sum of the two fractional values. It gives me a value of 0.09, so my solution is 0.42 plus or minus 0.09. And you notice there's no units there because I'm dividing kilograms by kilograms, so the units therefore cancel because it's a ratio. The last way of combining uncertainties I might come across is when I'm using powers. Here I multiply the percentage uncertainty by the power. Now here I use an example of the period of one pendulum has a swing of 3.4 plus or minus 0.2 seconds. What is the uncertainty of the period squared? So period squared is 11.6, but my uncertainty is 11.6, which is the value multiplied by 2 multiplied by the fractional uncertainty of the original value, which gives me a 1.4. So that gives me 11.6 plus or minus 1.4 seconds squared. I've gone through this quickly. You'll need to review these points as and when you need them whilst doing experiments. But I hope this was useful.